21,196 kilometers of stone-built dragon, 28 million cubic meters of concrete barrier, a 50-kilometer artery beneath the sea. Behind these numbers lies humanity's ultimate ambition, to confront nature, to cross impossible gaps, and to redraw the map of civilization itself. Today, we are not here to talk about meaning. We are here to dismantle the hard mechanics, to break down the mega-projects that consumed unimaginable amounts of human labor, material, and capital. China Great Wall. Seen from the vast interior of the Asian continent, those razor-sharp mountain ridges above 1,000 meters in elevation reveal the scale of a problem ancient China chose to confront head-on across 15 provinces. Humanity assembled its most colossal undertaking, a Great Wall. That continental-scale decision immediately raises a measurement challenge, and when viewed from orbit, the answer becomes unavoidable in length, mass, and exposed surface area. This structure stands as the absolute peak of human construction, the largest artificial form ever placed on Earth. That overwhelming scale also explains a striking illusion. 60 million visitors each year only experience the 80 kilometers near Beijing, while satellite maps expose the hidden reality of a stone dragon stretching uninterrupted across 15 provinces. That gap between what was seen and what truly existed defined modern understanding, until 2012, when drones and ground-penetrating radar revealed a buried system unseen for millennia, shattering the long-held belief that the wall measured only 6,700 kilometers. The revised figure of 21,196 kilometers reframes everything, multiplying earlier estimates by 4 and reaching nearly half the Earth. Circumference, a distance that would demand 2 full years of walking for a healthy adult, moving 8 hours a day. Confronted with how such distances could endure for 2,000 years, the answer lies inside the walls themselves, where ancient builders mastered a technique that turned earth into stone by reinforcing rammed soil with reed layers that strengthened the core while allowing moisture to escape. That internal structure becomes even more remarkable on the Lost Plateau, where clay mixed with crushed snail shells released calcium carbonate, forming a natural cement that hardened the walls to the point that even artillery could not break through. Such material innovation became urgent under a new constraint, as Mongol cavalry pressure forced Ming engineers to achieve the unthinkable, constructing 8,500 kilometers of wall in just 70 years, a pace almost unimaginable in the pre-industrial world. Meeting that timeline depended on a production choice visible in every segment, as oversized bricks 4 times larger than standard units, each weighing 10 kilograms, accelerated assembly while locking together a total of 4 billion bricks. Supplying bricks at that scale required an entire industrial ecosystem, with 271 kilns operating non-stop, teams of 20 workers per kiln, and outputs reaching up to 10,000 bricks per F-ring, transforming the region into an ancient industrial complex. That relentless output introduced a cooling constraint, solved through rapid quenching that not only sped production, but altered chemistry, preventing iron oxides from turning red and leaving the bricks with their distinctive blue-gray color. Even with bricks and earth explained, the true binding force remained hidden inside the mortar, where Ming craftsmen unknowingly created a composite stronger than modern cement, using an ingredient found in everyday kitchens. Sticky rice provided the missing mechanism, as branched starch molecules locked calcium carbonate in place, producing mortar that stayed rigid outside, flexible within, survived extreme cold, and even healed erosion over time. With materials, methods, and scale still being uncovered, the figure of 21,196 kilometers now feels provisional, as some researchers estimate the true extent may reach 50,000 kilometers, leaving vast underground remnants as unanswered chapters of ancient ingenuity. China 3 Gorges Dam. This scale of ambition could only exist where energy demand had already reached a breaking point, and that pressure explains why a 17-year construction effort involving 40,000 workers rose directly from the Yangtze River as a project that stunned the world. That explosive growth in power demand meant traditional sources could no longer keep pace. So China turned its attention to the Yangtze River itself, where a single massive dam could concentrate energy production at an unprecedented scale. Once the river itself became the foundation, the challenge shifted to sheer material scale, demanding 28 million cubic meters of concrete, enough to form a 1-meter-wide solid pipeline wrapped entirely around the Earth. With that concrete mass locked into place, the interior space could finally be filled with power generation systems, leading to 32 turbines, whose combined output can supply electricity to 60 million people across China. To install those systems inside a flowing river, engineers first had to divide the Yangtze itself, constructing 3 cofferdams to redirect water and allow segmented construction on a temporarily dry riverbed. After sealing the river back in place, thermal stress emerged as the next threat, forcing engineers to cool aggregates, add ice, and deploy mist spraying systems to prevent internal cracking in the massive concrete body. With structural stability secured, attention turned to navigation, resulting in the world's largest ship lock and an elevator-style ship lift that reduces a 4-hour journey for 3,000-ton vessels to just 36 minutes. That navigation upgrade was inseparable from flood control, as the reservoir can store 22 billion cubic meters of floodwater, transforming disasters expected once every decade into events closer to once every century. After integrating power generation, flood control, and navigation into a single system built on more than a century of accumulated expertise, a new question emerges around whether such complexity can remain risk-free over time. That long-term risk becomes visible in seasonal water fluctuations that limit real-world generation efficiency to 45%, raising the possibility that artificial intelligence scheduling may be the only way to unlock the dam's full potential. Channel Tunnel. This idea survived for 6 centuries precisely because it looked too dangerous, too expensive, and too disruptive to execute. When it finally became a 6-year sprint that burned through $15 billion and nearly dragged down 2 nations, the Channel Tunnel was no longer a plan on paper. It was a high-stakes gamble that people still call a modern wonder. From the 1802 carriage tunnel concept to the 1974 effort that was stopped halfway, the project kept dying for the same reasons: invasion paranoia in Britain and governments that could not afford the bill, leaving the tunnel to feel like an impossible task with a curse attached. That political green light only mattered once the financing model shifted the risk away from governments. Private funding revived the project, yet the price tag exploded from $3.5 billion to $15 billion, with some reports pushing the total as high as $21 billion, turning the tunnel into a money furnace with no obvious limit. That financial pressure meant the engineering schedule could not afford hesitation once digging began. 11 giant tunnel boring machines launched from both shores, with Britain driving 22 kilometers and France 15, all racing toward the midpoint known as Point M, until the first weeks exposed a crisis that could have ended the entire effort. That early crisis traced back to a single assumption about geology and machine design. The British bet on a dry route and used equipment that was not waterproof. Then water arrived like a Niagara, scale leak at 300 to 400 liters. per minute, while cracks began to appear in the tunnel crown, where failure is unforgiving. That repaired ceiling came at the cost of 3 months of non-stop struggle, and the worksite never returned to normal. That human toll was only one part of the physical footprint the tunnel created on land. With 4.9 million cubic meters of spoil and nowhere to put it, that growing evidence of scale and sacrifice made the alignment moment the only true pass-or-fail checkpoint. After 50 kilometers of blind drilling, the two sides met with just 35 centimeters of error, a margin so tight that a small miss could have erased years of work, and it was earned by the sweat of 13,000 workers behind that handshake. That precision only mattered once the tunnel proved it could carry real traffic at scale. Since opening in 1994, 430 million passengers and 86 million vehicles have moved through it, cutting London to Paris, travel to about 2 hours, and shrinking the old sea and land route by roughly 2/3, while the operator now reportedly clears 1.4 billion euros a year. That long arc from doubt to profit turns the tunnel into more than a technical achievement. It becomes a template for cross-border cooperation under extreme constraints. A 50-kilometer link that once looked impossible now anchors European connectivity. Egypt-Suez Canal. This narrow blue corridor, cutting through the Egyptian desert, is already defined by one unavoidable fact: a 190-kilometer artificial waterway that has separated Asia and Africa for more than 150 years. That physical separation alone reshaped global shipping routes, turning this into far more than an ordinary canal. Yet the conditions under which it was built would leave scars of delay, sacrifice, and conflict that never truly disappeared. That human cost became the defining constraint when construction began in 1859, with tens of thousands of laborers dying under desert conditions and excavation relying almost entirely on hand digging and shoulder hauling. Only after industrial age excavation machines emerged did this collapsing manpower system gain enough mechanical support for the project to move forward at all. With machinery finally forcing the route open, 10 years of struggle produced a 164-kilometer passage that rewired global distances, cutting the Europe-Asia sea route from 19,000 kilometers to just 8,000 and slashing travel time in half. This dramatic efficiency gain transformed world trade overnight, while quietly setting the stage for new problems tied to control, security, and geopolitics. Control over this strategic shortcut soon turned efficiency into vulnerability, as the 1956 nationalization triggered military confrontation, and the 1967 Six-Day War converted the canal into a front line. For 8 years without maintenance, sunken ships, naval mines, and encroaching sand reduced this once critical artery to a paralyzed trench. Even after reopening, the original canal layout remained constrained by a single-direction system, a limitation that became impossible to ignore as container ships grew ever larger. In response, Egypt launched a 72-kilometer parallel channel in 2014 to enable two-way traffic, assigning this pharaoh scale upgrade a brutally short deadline of just 1 year. Meeting that compressed schedule meant confronting sheer volume, with 500 million cubic meters of sand to be removed, equivalent to the mass of 200 Great Pyramids of Giza. This task fell to the world's most advanced cutter suction dredgers, steel giants operating non-stop to carve a second lifeline straight through the desert. The expanded channel immediately converted excavation effort into measurable performance gains, cutting transit time from 18 hours to 11 and reducing waiting time from 11 hours to just 3. Capacity effectively doubled, now supports a system carrying 8% of global maritime trade, where a single 18,000 container ship can pay tolls reaching $800,000, making the Canal Egypt's third largest source of income. Yet the system remains unfinished, with a 4-kilometer underwater tunnel next in line, extending a pattern in which this canal is never truly complete, only continuously rebuilt. Italy-Venice Flood Barrier System, MOSE. This fragile balance between a city and its surrounding water has reached a breaking point after decades of strain. A 20-year construction effort and a €73 billion investment now stand against a city that was born on water, yet is being slowly forced toward extinction by it. The flooding seen at street level is only the visible result of deeper forces acting below the city. Over a century, Venice has sunk 25 centimeters, while sea levels have risen another 13, turning ordinary tides into disasters, with excessive groundwater extraction accelerating the collapse from beneath. That historical warning made it clear that passive endurance was no longer an option for the lagoon. Under mounting pressure, the MOSE project emerged as a last resort solution, deploying 78 mobile floodgates across 3 sea inlets to form a movable seawall, even as hidden risks were already embedded in its design. The scale of that ambition immediately collided with unprecedented engineering constraints. Each 12,000-ton concrete caisson had to be lowered onto the seabed with extreme precision, forcing engineers to invent the largest synchronized lifting system in the world, where errors were measured in millimeters rather than meters. Those precision demands did not end once the foundations were set in place. At depths of 20 meters, underwater tunnels had to remain waterproof and accessible for maintenance, while all 78 gates were required to rise and fall in perfect unison, a challenge comparable to assembling building blocks on the ocean floor. Once the hardware was finally in place, the system shifted from construction to decision-making under pressure. The control center must issue a final command 3 hours before high tide, where a delay of even 1 second can mean failure. Yet this operational tension exposes an even more dangerous vulnerability. Operating the gates raises consequences that extend far beyond flood protection itself. Polluted, dredged sediments, newly created 49 kilometers of artificial beaches, and the repeated closure of the lagoon threaten to disrupt water exchange, risking a transformation of the ecosystem into stagnant water. All of these unresolved risks converge as the project nears completion after 2 turbulent decades, with sea levels continuing to rise and annual closures potentially reaching 200 times per year. The €73 billion seawall faces a final question that no engineering chart can fully answer. Can it truly save Venice? Italy Leaning Tower of Pisa. 199 years. The longest bell tower project ever attempted. Construction began in 1173 and somehow turned into the most awkward engineering accident in architectural history. The name Pisa itself traces back to a word meaning marshland, and this former bog was never meant to support a massive tower, a 57-meter structure, standing on a foundation barely 3 meters deep. Once that shallow foundation met soft, waterlogged soil, the problem stopped being slow settlement and became runaway imbalance. The ground began sliding sideways under the load, an ending that was effectively written on day 1. With the soil already yielding, every added layer made things worse. 14, and 1,000 tons of stone pressing into a 3-meter soft foundation, like building a skyscraper on a sponge. As the weight kept amplifying the lean, the real danger was no longer the tilt itself, but the loss of control. By 1990, the angle passed 5.5 degrees, crossing the collapse threshold. The tower was shut down in an emergency. With alarms already flashing red, The instinct was to harden the foundation. But soft soil isn't an empty void. You can simply fill. One of the most disastrous rescue attempts ever. Mussolini ordered 90 tons of concrete poured in, making the tower sway even more and nearly pushing it to collapse. After grouting backfired, engineers tried locking the soil in place by force. But once the underground system was disturbed, it reacted brutally. 40-meter boreholes and liquid, nitrogen freezing led to severe shrinkage after thawing. Overnight settlement equal to an entire year. The tower edged closer to disaster. When reinforcement and freezing only created new risks, the only controllable variables left were time and weight distribution. After 10 years, engineers stopped forcing resistance and instead removed soil slowly, letting gravity do the correction. The tilt was finally brought back into a safe range. The tower is back within the safety zone, but the soft foundation that caused everything never went away. Today it still leans at 4 degrees, yet is expected to stand for another 300 years. But is this truly the final answer? If the ground shifts again, can humanity save it one more time? Italy Milan Cathedral. The longest running megaproject ever built. From its foundation to completion, the construction stretched across 630 years, 547 years of actual building, passed down through generations. Yet almost no one lived to see it truly finished. A timeline this long wasn't slowed by design first, but by materials. Terracotta proved structurally inadequate, forcing an emergency switch to pink marble. And even entire canals had to be dug just to transport it, because normal roads simply couldn't handle the load. Once materials, transport, and structure were pushed to their limits, authorship itself became the real uncertainty. 78 of Europe's top architects took part. Even Leonardo da Vinci submitted a dome proposal, only to withdraw it midway. The cathedral never had a final, agreed-upon vision. When outside criticism directly challenged the project's scientific basis, the builders were forced to confront their own technical limits. One poorly grounded accusation unexpectedly triggered major upgrades in tools and construction methods, wrong in theory, but effective in practice. With engineering slowly catching up, the cathedral's true ambition became clear. Covering 100,000 square feet, rising 354 feet high, and capable of holding 40,000 people, it ranks as the world's 5th largest cathedral, yet it began earlier than nearly all of its peers. Once structural scale could no longer expand, ambition shifted into detail. 135 spires, each crowned with a statue, topped by the golden Madonnina. To this day, Milanese locals judge the weather by whether they can see her. The cathedral was officially declared complete in 1965. Yet large sections of stone were never carved at all. A structure spanning 6 centuries may never have been a finished project, but a history that is still unfolding. Cambodia, Angkor Wat Temple Complex. This is the kind of engineered civilization that should not be able to vanish quietly. Yet Angkor did exactly that. A super project that stretched across 6 centuries, supporting a metropolis of nearly 1 million people, still ended up swallowed by jungle silence, leaving one question hanging in the air. What kind of system collapses so completely that it erases itself? That mystery becomes sharper once the true scale of the city is visible on the map. With an area comparable to modern Los Angeles, it was the largest pre-industrial settlement in human history. And the sheer logistics of feeding, moving, and building at that size would challenge modern engineers. The logistical burden implied by that scale demanded extreme construction discipline, and Angkor delivered it. 300,000 workers spent 40 years fitting stone so tightly that not even a sheet of paper could slip through. Yet the real miracle that kept the city alive was not the carving, It was the water system underneath everything. That hidden dependency on water becomes concrete when the reservoirs and gates come into view. An 8-kilometer long 2-kilometer wide mega reservoir dug by 6,000 people over 6 years with hand tools turned Cambodia's harsh wet and dry seasons into a controlled cycle. Yet this engineered empire unraveled due to a 20 to 30-year mega drought and religious shifts that diverted maintenance from water infrastructure. Today, the same threats, water seepage, jungle pressure, and massive tourism, reemerge. Modern engineers struggle to save it. With 3,000 to 5,000 Daltons, illy visitors eroding ancient reliefs, creating a tough choice between protection and development. Twice a year, the sun's aligned beam into the ritual chamber reminds us, can modern engineering keep this sacred super project alive for another millennium? India Delhi metro system. This massive network already hints at a system built under constant pressure, rather than ideal conditions, spanning 400 kilometers with nearly 300 stations. One of the world's largest metro systems still needed 20 years just to reach a basic form, raising the question of what structural obstacles slowed it at every step. That promise of scale immediately collides with the reality of access. Fares, starting at 10 cents, still exclude millions of residents, while the expansion of the metro has quietly displaced even cheaper bus systems, turning a solution for congestion into a new layer of inequality. That gap between intention and experience becomes physical inside the system itself. Transfers between lines can require walks of nearly 1 kilometer, the longest in the world, exposing how separate construction phases fail to align despite being part of a single master plan. That fragmented layout above ground mirrors the constraints buried below it. To avoid a 16th century monument, a stalled tunnel boring machine forced workers back to manual rock cutting, a collision of ancient heritage and modern transit that consumed months of lost time. That vulnerability deepened when construction uncovered the remains of the Akbar Mosque. The line had to shift 45 meters. Tunnels were extended by 72 meters, and the schedule absorbed a 6-month delay simply to protect what lay underground. That single detour was not an isolated incident within this ground. When a tunnel boring machine pierced an ancient well, it triggered a 172 cubic meter cavity, demanding 24 hours of emergency repair to prevent collapse, one of many disruptions that repeated across the project timeline. That accumulation of underground limits pushed complexity upward into the air. A 23.6-meter elevated crossing over the Airport Express required a custom 4-step lifting method, forcing engineers into precision maneuvers just to thread new structures between existing ones. That vertical struggle continued at the scale of individual stations. The world's shortest metro station, at just 150 meters, exists only because land acquisition failed, cutting its length in half and forcing designers to stack every function upward instead of outward. 4 construction phases, spanning 20 years, continue to push toward a system designed to carry 10 million passengers a day, leaving one unresolved question: can expansion finally fix problems that were embedded from the very first tunnel? The destination of these projects was never simply completion. They are living history, a dialogue between humanity and the planet, a negotiation between ambition and its cost. Every wonder we examine today hides the same underlying truth. The greatest engineering achievement is always the next one, and the hardest challenge is learning how to coexist with the world we have built ourselves.